Hey everyone, and welcome. Have you ever wondered how you can take one single physical network, the same switches, the same wires, and somehow split it into multiple, completely separate virtual worlds? Well, that is the magic of network segmentation, and that's exactly what we're going to break down today.
All right, so check this out. We've got three computers here, PCA, PCB, and PCC. They're all plugged into a couple of switches, so physically they're on the exact same network. But here's the weird part. PCA can talk to PCB with no problem, but for some reason, neither of them can get a signal to PCC. So what's going on here? How is that even possible? Well, that's the mystery we're about to solve.
So, to really get what's happening in our puzzle, you first have to understand what a basic or flat network is like. In that kind of setup, there are basically no internal walls. It's kind of like one gigantic open plan office where every single conversation, every little whisper is broadcast to everybody. It's just noisy, it's chaotic, and there is zero privacy.
And, that chaos creates a couple of huge problems. First, your performance just tanks, because all that unnecessary chatter is clogging up the network. And second, and this is way more important, you have absolutely zero internal security. If one person's computer gets a virus, it can literally spread like wildfire to every other machine in the blink of an eye. We've got to find a way to build some walls.
And that's where our first tool comes into play, the virtual LAN, or as you'll always hear it, the VLAN. You can think of VLANs as the digital way to build walls inside our network, creating these separate, secure rooms. This is exactly how places create a separate guest Wi-Fi, or how they isolate their sensitive credit card processing systems from everything else.
So what is a VLAN, really? At its core, it's a technology that lets us take one physical network and just logically slice it up into as many isolated virtual networks as we want. What's so cool is that even if devices are plugged into the very same switch right next to each other, if they're in different VLANs, they might as well be on different planets. They can't see each other, they can't talk to each other. It's that simple.
I love this analogy because it makes it super clear. Imagine your physical network is one huge open warehouse. A VLAN is the tool that lets you go in and build walls inside that warehouse, turning it into individual secure office suites. The sales team gets their own suite, engineering gets theirs, and so on. They're all in the same building, sure, but their business is kept private.
Okay, that makes sense. But how does a computer or a printer actually get into one of these virtual office suites? Well, it connects through a switch port that's been specially configured as an access port. And this is the key thing to remember. An access port belongs to one and only one VLAN. It's like a doorway that only opens into a single specific office.
All right, so we've created our separate office suites, our VLANs. But what happens when our company gets bigger and we need a second building? Or, in our world, a second switch? How do we make sure the sales team in Building A can still talk to the sales team over in Building B?
Let's bring this back to our diagram. PCA is in our student VLAN, and it's on one switch. PCB is in the same VLAN, but it's on a different switch. Now, we know we can't use an access port to connect the switches, right? Because an access port only knows about a single VLAN. We need something more powerful.
What we really need is some kind of superhighway between our switches, a special link that can carry the traffic for the student VLAN and the faculty VLAN and any other VLAN we might create, all at the exact same time, without ever getting them mixed up. And that special connection has a name. It's called a trunk.
This chart just lays out the difference perfectly. An access port is your specialist, one single VLAN connecting to an end device like your PC. A trunk port is your multitasker. It carries traffic for multiple VLANs and connects switches to each other. Remember the analogy? Access ports are the doors to the rooms. Trunk ports are the hallways that connect all the different buildings together.
Okay, this brings up a really interesting question, right? If all this different traffic from all these different VLANs is flowing down the same hallway, the same trunk link, how on earth does the network keep it all straight? How does it know which data belongs to the students and which belongs to the faculty? Well, the answer is a really clever bit of digital labeling.
The solution is actually super elegant. As the piece of data gets ready to travel across that trunk link, the switch it's leaving from attaches a small digital tag to it. And this tag acts just like an ID badge, clearly stating, hey, I belong to this VLAN.
And get this, this isn't some secret sauce from one company. It's a global standard.
It's called IEEE 802.1q. And, as the standard itself says, its entire purpose is to define the format for that digital tag, so that switches from Cisco, Juniper, Aruba, you name it, can all speak the same language and understand each other.
So what's actually in this little digital ID badge? Well, two main things. First, and most importantly, is the VLAN ID, or VID. That's the number that says, this data belongs to VLAN 10, or this is for VLAN 20. The second part is a priority code point, which basically tells the network how important this piece of data is. It's how the network can prioritize something like a live video call over a simple file download. Pretty cool.
Okay, let's walk through the whole journey. A piece of data leaves your PC and travels to the switch. Right now, it's untagged. The switch sees it came in on an access port for, let's say, VLAN 10. So boom, it slaps an 802.1q tag on it with the VLAN ID of 10. Next, that newly tagged data zips across the trunk link to the other switch. That second switch reads the tag, sees VLAN 10, and knows exactly where it needs to go. And here's the final brilliant step. Right before sending the data out to the destination PC, the switch removes the tag. The PCs and printers at the end have no idea any of this tagging ever happened. It's all done behind the scenes.
Okay, we have covered a lot of ground: VLANs, access ports, trunks, and tagging. Now, let's tie it all together and finally, officially solve that puzzle we started with.
All right, let's look at our network one last time. We've got PCA and PCB in the student VLAN, which is VLAN 10. Then we have PCC all by itself in the faculty VLAN, VLAN 20. And that link between the switches? That's a trunk, carrying traffic for both. Now we can finally understand what's happening.
And now it all makes perfect sense. PCA can ping PCB because they are both members of the same virtual world, VLAN 10. That trunk link between the switches makes sure their conversation can happen. But PCA and PCB cannot ping PCC. Why? Because PCC is in a totally separate, isolated world, VLAN 20. The digital walls are up, and they are working exactly as they should.
So, when you boil it all down, network segmentation gives us three huge wins. First, security. A virus on a student computer is trapped inside the student VLAN. It can't jump over to the faculty network. This is huge for things like isolating guest Wi-Fi. Second, performance. All that broadcast chatter is contained within its own VLAN, so things run a lot smoother for everyone. And third, organization. We can group our users by department, not by where they happen to be physically sitting in the building.
And that brings us to a final, pretty important thought for today's world. In modern cybersecurity, there's this big idea called zero trust, which basically means never trust, always verify. You just assume no part of your network is truly safe. And in a world like that, doesn't creating these small, isolated virtual segments, these VLANs, become one of the most powerful first lines of defense you can possibly build? Something to think about. Thanks so much for joining us.